Hey AP Chemisters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. We start today with section 16.2 and it's all about buffers. And I really hope that you have read this section very carefully. If you see what I wrote on the notes, that this is a very important section. I don't know how much I can really emphasize that. Another one's coming up in 16.4, another very important section. This chapter is really an important one and don't take it lightly. Okay, so I ask you to please read, focus, do all the homework. It will be on the AP guaranteed. So as always, let me just remind you that when I ask you to pause, you need to pause and do the work. I hope you have a calculator with you. Jot down any questions you might have. You know the drill to make this the most effective way possible. So anyway, let's talk about buffers. What is a buffer solution? It's a solution that resists changes in pH when either hydroxide ions as a base or protons in the acid are added. So remember, hydroxide's OH minus, protons would be the H plus. What makes up a buffer? It's a significant amount of a weak acid and its conjugate base, or it can be a significant amount of a weak base and its conjugate acid. So there are several examples that I'd like to talk to you about as far as examples of a buffer. Very important. So if you remember back when we did the pH scale on the blank wall, I told you about Soren Peter Sorensen and how he was hired on by a Swedish brewery to determine which batches of beer went bad. And a batch of beer that went bad is too acidic. And so what do we have today to prevent our food from going bad? From our soft drinks and I suppose our beers. I don't check beer labels to tell you the truth. What is it out there that preserves the acidity of the different solutions? And it's a buffer. So here I have a Mountain Dew. I actually had a can of Mountain Dew, or actually a bottle of Mountain Dew on my desk, so I thought I'll just take a picture of it. So here it is. All right, so you can see over here that my Mountain Dew container has carbonated water, high fructose corn syrup, concentrated orange juice, citric acid, natural flavor, sodium benzoate, caffeine, sodium citrate. So right here, check out your citric acid and check out your sodium citrate. Here is your weak acid. Here is the conjugate base. Here is your salt of the weak acid. So this right here in your Mountain Dew sets up a buffer. And why would they put that in there? You are preserving the acidity of the drink. Okay, what would happen if they didn't put that in there? Well, you might open up the can one day and realize that, ooh, it tastes nasty. Why would it taste nasty? Well, maybe because it was too acidic. Okay, so let's go back to the front page. And I actually wrote out, so here are the ingredients. So carbonated water, high fructose corn syrup, so notice there's a lot of sugar there, not too good to drink. Orange juice, citric acid, and sodium citrate. What do you notice? We have what's citric acid? A strong acid or a weak acid? Hopefully you know by now it is a, Saved by the Bell. Hopefully you know it is a weak acid. And this is its conjugate base. Don't worry about the sodium. We already learned that sodium does not affect the pH of a solution, but the weak or the conjugate base sure will. Okay, so we have a buffer in the Mountain Dew. So why do you suppose those ingredients are there? To preserve the pH. You don't want that drink to get too acidic. It's going to burn your throat going down. That'd be bad. You don't want that pH to change or it's going to really affect the taste. Okay. We have another very important buffer system in our blood. It's composed of carbonic acid. Hey, isn't that what carbonated water is? Carbonic acid. Isn't that how you make carbonic acid? Yes, it is actually. And bicarbonate ions. So wait. You're telling me my blood has carbonic acid and sodium bicarbonate basically get it basically, in my blood? And the answer is yes. And it has such an important function in your blood. What would happen if you have a buildup of too much acid in your body? And that's actually a condition called acidosis. And it could kill you, to be honest, all right? If you have acidosis, it could kill you. So your body has a natural way to prevent that from happening. Now, how do you get acidosis? Well, one way, which I do not recommend, please don't do this at home, is holding your breath. Well, why is holding your breath one way to make acidosis? Well, you are not breathing out your carbon dioxide, so you have more and more carbon dioxide in your body because you're not breathing it out, and it is going to react with the water in your body, which you have a lot of water in your body, and you're going to make more and more and more carbonic acid. And eventually, what's going to happen if you hold your breath? Well, you're going to faint. Okay, and that is your body's natural response to get you breathing again, and that way you can expel the carbon dioxide. But in the meantime, you're fainting, you're getting lightheaded, and that's because of the buildup of the acid in your body. So that's bad. But what's in your body? So if you want to drink a thing of lemonade, or you want to drink some Mountain Dew with all that acid in it, why don't you die of acidosis then? Well, you have buffers in your body to prevent the pH from changing drastically by drinking a pop or by eating a grapefruit or something. So it's a really good thing that you have these buffers. Now, if more base is added in the blood, then the weak acid will neutralize it. Your carbonic acid will neutralize it. If more acid is added to the blood, then the conjugate base will neutralize it. And so that is your body's way of resisting change in pH. All right, so let's check out problem number 1. Here we go. Which solution is a buffer? Okay, go back and remember that definition, and you pick. Pause this if you need to. Okay, I got letter D. A solution that is 0.100 molar in HNO2. What do you know about nitrous acid? It's a weak acid. It's not one of the big 6. And here's your sodium nitrite. What's wrong with A? Well, number 1, we have a strong acid. That's a big clue there. And number 2, they aren't related. It's not a weak acid and it's conjugate. What's wrong with B? We have an acid and its conjugate base, but nitric acid is strong. Bad news bears. Letter C, what's wrong with this? Nitrous acid is a weak acid, but this is not its conjugate base. Sodium chloride is a neutral salt. So it leaves us with D. Here we have a weak acid and its conjugate, like we had citric acid and sodium citrate. All right, so how do we calculate the pH of a buffer solution? Please, 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 if you haven't already, get out your calculators right now, okay? And it says, consider a solution that initially contains 0.100, I said it right, 0.100 molar of acetic acid and 0.100 molar of sodium acetate. And so here I set this up. I have my initial conditions. And the question is, what is the effect of adding more acetate according to Le Chatelier? So what if I increase this right here? Well, what's going to happen? It's going to shift to the left is correct. So equilibrium will shift away from the added component. It's going to shift over here. So by shifting left, what happens to the amount of hydronium ion? It's going to decrease because it's going to shift to the left. So if it decreases, that means I have less acid, so pH is going to be higher than expected. Remember, if you lose the acid, the pH goes up. Okay, let's go to the next page. So it says, calculate the pH of a buffer solution containing both the acetic acid and the sodium acetate. And there's the Ka value for you. And when you set up this equilibrium expression, keep in mind you have both the acid and its conjugate base there. Now, how did I know to put the acetic acid on the reactant side, if you will, and the acetate ion on the product side? Well, what I would do if I were you is I'd look over here. They gave you the Ka. So you're talking about the acid. So put your acid, your acetic acid, on the reactant side, and put your acetate on the product side. And so if you go through, well, what do acids do? They donate. So here's your HCO+, and then here's your acetate ion. So what's the next thing I should do? I should set up my initial conditions. Tells me I have 0.1 molar and 0.1 molar. They have the same molarity. Notice I don't start off with any of the hydronium ion. And then what? Well, I know it's going to shift, but what direction is it going to shift? Don't forget about your Q. Q is going to come up again at the end of this chapter. Hopefully you read about that. And don't ever forget. So Q is products over reactants, and so 0 over anything is 0. It's going to shift to the direction of your 0. It's going to shift right. Oops. So don't forget about that. Here, let me put it over here. It's going to shift right. I probably won't refer back to it again, but it's always something good to remember. And so because it's going to shift to the right, it's going to go like this. And when I'm all done, I'll have this value right here. Now, I'm not done yet. I still need to calculate what X is to calculate pH. So we're going to go back and look at our Ka value. Again, remember that was my hint. I told you to set it up this way because we have a Ka. And this time we have a value of X as your H plus ion, your hydronium ion, and here is your 0.100 plus X, your 0.100 minus X, or products over reactants. And what do we know? Well, let's assume, because look at this value right here, 10 to the negative fifth, that hopefully our approximation is good. So I can actually cancel out these guys here. And now what do you notice? We have X times this divided by the same number. Can I cancel those two out as well? Yes, you can. So what does that leave us with? X. So X is equal to Ka. Let's check that out. Yes, it is. Okay, so if X is equal to that value, what is X equal to? Go back here. What's X? This is so important. I can't emphasize this enough. Go back and look at what your X is. X is your hydronium concentration. Because that's what X is, you can now solve for pH. What's pH? Is a negative log of that number. Okay. It might not be a bad idea at this point saying, okay, so what did this buffer do for me? This buffer resisted the change in pH. So what if we didn't have the bicarbonate here? I'm sorry, the sodium acetate here. What if that was not there? What if we only had this present? All right, could you figure out what this is equal to? It's probably oh, I don't know, X squared. Let's see here. Let me kind of do some quick math here. X squared over 0.1 is equal to 1.8 times 10 to the negative fifth. So X squared is equal to 1.8 times 10 to the negative sixth. You're talking about X is equal to something but like 1 times 10 to the negative third. And if that's the case, if X is equal to something times 10 to the negative third, I'll just kind of quickly jot this down here, the pH is roughly 3. Okay, so the pH would be roughly 3 if this were not present. But because that molarity of the sodium acetate is there, look at that, the pH, it's less acidic. So what happens is that this conjugate base is kind of, in a sense, making this less acidic. Why? Because what's really happening, we're not going to shift as far to the right anymore. We're actually going to kind of go back this way, decreasing the amount of hydronium ions that we're really producing. So without this here, we would produce 10 to the negative third molarity of hydronium. With this already present, we are producing 1.8 times 10 to the negative fifth. So we're actually like decreasing the amount of the hydronium ion by about 100, 10 to the second, because we have that conjugate base present. Okay. All right, let's try the next one. Let's try number 2. Ready? I'm sorry, I forgot one little thing. Before we go on, it's always good to check to make sure approximation is good, especially because it is to the negative fifth. So I just quickly went, what's 5% of 0.1 is 0.005. That number is definitely bigger than this number. Our approximation is good. And you don't forget about this, but really, especially with these buffers in place, it's not really going to become an issue. So we won't have to use the quadratic at all in this section. Yay! Okay, now let's go on to number 2. All right, so calculate the pH of a buffer containing 0.200 molar of acetic acid. And can you do me a favor? Make this 0.100 again. I'm sorry, that is a typo on my part. 0.100 molar of the sodium acetate. So now what's going to happen? These two numbers are not the same. Remember how so nicely they cancel each other out up ahead? Notice how these numbers canceled out when they were the same molarity, and that's actually a point we're going to come back to in the next section. But for right now, we're going to change the amount so we don't have equal amounts. So before we begin, let's think. What do you have more of? Do you have more acid or more base? Well, hopefully you figured out we have more acid than base. So what do you think is going to happen to the pH? The pH is going to be reflect, it's going to be more acidic. So I would expect when it's all said and done, my pH should drop by very much, not by very much, but some. So I should have a number less than 4.74. So keep your eye on this and let's see how we do. All right. Well, we have, here's my initial amount. Notice again, I changed that, so it's 0.100. Otherwise, you get the same exact number again. And again, Q is 0, so it's going to shift to the right. And we can set up this. Okay. So we can have a Ka value, a Ka value, here we go. And this time, what can I cross out? Well, I can cross out these guys because of that 1.8 times 10 to the fifth, but can I cancel out these guys? No. So what is that going to be equal to? 1.8 times 10 to the negative fifth. Again, if I'm going too fast for you, you can always pause this and catch up. And this time solve for x, okay? It's not equal to 1.8 times 10 to the negative 5, but what do you notice? X is equal to 3.6 times 10 to the negative 5, because this is really 1 over 2, multiply both sides by 2, and that's 3.6. And what is x equal to? How many times do I say this? Go back, and refer back to what x is. It's right here. It's your hydronium concentration. Very important, because all you have to do is then click your negative log, and voila, there's your pH. What do you notice? This is indeed less than 4.74. So what is my conclusion? I'm going back and looking at this number again. Because more of your acid was present, you had a higher concentration of the acid than the conjugate base, you're going to, in a sense, shift to the right, okay, making more of the H3O plus. Notice that the 3.6 times 10 to the fifth is bigger than the 1.0 up in the first question. And so you will have a lower pH. Okay, so that's how that works. And now let's do problem number 3. Okay, so here you calculate the pH of a solution containing 0.75 molar of lactic acid and 0.25 molar of sodium lactate. Lactic acid is a common constituent in biological systems. If you are working out and your muscles are really getting tired and they hurt, you probably have a buildup of this lactic acid. So why don't you go ahead and pause this, work this whole problem through, and see how you do. Okay, I hope you got a good answer. Let's see what happens. How come I start off with this way? Once again, what was my clue earlier? I gave you the Ka. So what should you write first? The acid. Put the acid here. Make it an acid. And so you're going to make in the hydronium ion and the lactate. What is our initial set? Here we go. It is going to shift to the right because Q is 0. And you're going to see we have this value here. Now we need to solve for what x is equal to. I'm just plugging in my values here. Again, what can I cancel out? I can cancel out these puppies here, and so all you have is this term. I think you can do that. And I'll go ahead and solve for x here. X is equals to 1.4, or I'm sorry, this term is equal to 1.4 times 10 to the negative fourth. So x is equal to 4.2. How did I do that? I multiplied this side by 3. And so that x is your hydronium concentration. Again, I told you to go back and look at that. And so, wait a minute, let's check this out. What's 5% of my initial value? It is 0.0375. And hey, what do you notice? That is much bigger than 4.2. So we are good to go. Our approximation is good. And so the pH is equal to 3.38. I sure hope you got something real close to that anyway. Does this answer make sense? Well, if you were just to look at this number, yeah, this is going to be an acid. But because I also have more of the lactic acid than the lactate here, it is going to, in a sense, make more of the hydronium ions. So it's a fairly acidic solution. Okay. Now, are you getting kind of tired of all these ice tables? Do you realize this is the 3rd chapter in a row that we are using ice tables? And the question is there an easier way? And what do you think the answer is? If I were asking, of course, the answer is an emphatic yes. So let's turn the page here, sorry about that, and see what our easier way is. All right, this equation that we're going to show you is called the Henderson-Hasselbalch equation. What a great name. I will probably abbreviate it as the HH equation, but it's the Henderson-Hasselbalch equation. Now, if you check out your equation sheet, if you would, go to where it says equilibrium. So if you need to pause this, find your equation sheet, and then find where it says equilibrium. Let's look at that. Okay, I hope you found it. And you will see that the Henderson-Hasselbalch equation is on the equilibrium section of the equation sheet. So this is not something that you have to memorize. You'll probably see it in this form right here. So where did it come from? Well, it comes from our initial idea of what is Ka. And if you take your Ka and solve for your H plus concentration, get H plus all by its side, this is what you're going to end up with. So let's take the negative log of everything. So the negative log of here, the negative log of this, and the negative log of the HA over A minus. So what do you know what the negative log of H plus is? It's pH. What's the negative log of Ka? It's the pKa. Now wait a minute. What happened here? What do you notice? It went from from a negative to a plus, but what also happened? It flip-flopped. So when you flip-flop, you take its negative and two negatives make a positive, and there you go. So this is how, to me, I'll phrase it. So pH is equal to pK plus a log of the base of the acid. The conjugate base over the acid, okay, or the base of the conjugate acid. It doesn't really make that much of a difference. For a particular buffering system, the acid conjugate base pair, all solutions that have the same ratio of the conjugate base and the weak acid will have that same pH. Let's check this out. Here's problem 2 continued. What do you mean problem 2 continued? Go back to the prior page. You'll see where problem 2 was. We're going to do the exact same equation as we did on the prior thing, but no ice table. Notice I didn't give you a whole lot of room, did I? There is no ice table, so let's use the Henderson-Hasselbalch equation, and here's your Ka. Well, let's check this out. Here's your pH is equal to pKa plus the log of base over acid. Will you go ahead and plug this number into your calculator? Take the log, in a sense, the negative log of that. Did you get 4.74? So let's plug that in. So here's pH. I plugged in the pKa, which again is a negative log of this number. Hopefully you see that. And then your base, which is right here. Here's your acetate ion on top. Your weak acid is on the bottom. And what do you notice about this right here? These guys cancel out. Did you check that out? So what is the log of 1? Well, go ahead, check this out. What is the log of 1? Hopefully you know that. It is 0. So the pH is equal to the pKa. And that's what they're saying right here. That's what this statement right here is saying. Is that if you have the same ratio of your weak acid and your conjugate base, then the pKa will equal the pH. And that's going to be an important theme when we hit section 16.4 too, by the way. So our conclusion is that the pH and pKa, they're equal because the molarities of your weak acid and its conjugate base are also equal. So let's go ahead and do problem number 3. So why don't you go ahead and use the problem 3 from the prior page, the exact same setup. You have the Ka value on page 2, and pause this and see if you get what I get. Okay, I hope you really did this and just not watch me. It's really helpful if you actually do the work instead of just watching me do it. So that way you can check your work, make sure you understand what you're doing. Well, as always, I would always start off with an equation, and this is a good one to write down. This time, what is our pKa? Did you actually plug in that value into your calculator and find that the pKa is 3.85? Hopefully you did. And then the molarity of your base, your lactate, is 0.25. Your molarity of your lactic acid is on the bottom, 0.75. And hopefully when you did that, now what's 0.25 divided by 0.75 is a third, or 0.3333. And what do you notice about the log of a number less than 1? It's a negative number. Okay, it's a negative number. So now I need to subtract both sides, or I need to subtract 0.48, and I get 3.37. And what's our conclusion? Well, I think on page 2, didn't we get 3.38? This is 3.37. It's a rounding issue. Man, we're really close. And so now I like this next question actually quite a bit, because what happens if I flip-flop the molarities of the lactic acid and the sodium lactate? Why don't you pause this and see what you get? Okay, well, very similar setup. Instead, what's on top? Well, the base is on top. The 0.75 is on top. Okay, the 0.25 is on the bottom. Well, what's 0.75 divided by 0.25? That's 3. And this is why I think math is so fascinating. I really do. I like math. You probably knew that, though. Look what the log of 3 is. Look at the number, 0.48, positive 0.48. What was the log of 0.33333? Negative 0.48. So what's really the only difference when you reverse the numerator and the denominator? You get a positive versus a negative. So notice 3 is bigger than 1. It's a positive number. Notice that 0.3333 is less than 1, so you get a negative log. Hopefully you made that observation. So this time the pH is 4.33. Now, does this make sense? I always ask that, don't I? Because chemistry really needs to make sense. So sodium lactate is your base. You have a greater presence of a base than you do of your acid. So what should happen to your pH if you have more base in it? Shouldn't it go up? Oh, it did, didn't it? Love it. Chemistry makes sense. All right. So let's go ahead and look at problem number 4. It says a buffer contains a weak acid and its conjugate base. The weak acid has a pKa of 4.82 and the buffer itself has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and the conjugate base in the buffer? Now, will you go back and look at the problem that we did here, the problem 3 number 1 and problem 3 number 2? Go ahead, look at those, and come up with your answer. Why don't you do this on your own? All right, see how you did. So I always start off with the equation. You should really get into that habit too. And what they tell us, well, that the weak acid, the pKa, is actually bigger than the pH, right? So the pH is smaller than pKa. So what does that mean about this number? What kind of number should this be? Is this going to be a positive term or a negative term if pH is smaller than pKa? Hopefully you realize you had to subtract a number to get a smaller number. So this term here must be negative. Well, in order for this to be negative, look at what's this. Is this term right here going to be bigger than 1, or is it going to be less than 1? Well, what did we say up above? We said up here at the first part that if the base is greater than your acid, you get a number bigger than 1, oh, like right here, like 3, and we end up adding it. That's not the case, though, is it? So what must be true? You must have more acid. We're going to put that, how about right here? You must have more acid than base. So little base, big acid. So this is going to be a number less than 1 to make the log term negative. So the ratio is going to be less than 1. And that is going to be letter A.